So the reactions I want to look at today may on the surface seem very different from each other, but I hope by the end of this you'll see that they all have something in common that may help you to be able to predict reactivity as we go forward. So all the reactions we're going to look at today give Markovnikov addition, and they also lead to products that are the result of anti-addition products. So regioselectivity is Markovnikov, so you get substitution or addition of hydrogen at the less substituted carbon, and you also see anti-addition during these reactions. So the first reaction I want to look at, and in all the reactions today we're going to use cyclopentene as our substrate. The first reaction I want to look at is the oxymercuration demercuration, where rather than our reaction that we've seen using either acid catalyzed hydration or adding of HX across the double bond, we're going to use mercury acetate in this case in water or with some water, and then we're going to follow that up with the addition of sodium borhydride at the end. The first step of this reaction, and in all these reactions that we looked at with alkenes, is the nucleophilic attack of an alkene on, in some cases, a Bronsted acid, a proton, in other words, or in the next few cases, we're looking at some kind of electrophile or some kind of Lewis acidic type position. And so just like our other reactions, if we were to do that here, we would see the addition of mercury as our Lewis acid side in this case. We would see our carbocation formation. What's unique about all the reactions today is that the attack, the first nucleophilic attack, results in the formation of a bond with a molecule that has a lone pair on it that can then come in and interact with the cationic charge that's been created. So instead of getting that second addition, what we see is a ring closure type reaction to form a three-membered cyclic intermediate. So in this case, it would look something like this, and we'll have both of them coming out at us in this case. So the positive charge is now moved to mercury. The advantage of doing this is that, one, it's very close to the cationic center, and that it helps to stabilize that positive charge. So now that positive charge is spread out over several atoms, not just isolated on carbon. So in this case, you get water coming in as our nucleophile, and we would see the anti-addition of water across the double bond. So we would get our anti-addition product added here with hydrogen coming out at me, and we would also see the enantiomer here. So another reaction that may not seem very similar to this at all, but actually is very similar, is just the bromination or chlorination reaction. So if we take an alkene and we add pure bromine to that alkene, again, we're adding a nucleophile, we're adding an electrophile in the first step, because remember we can polarize that bromide bond, that bromine-bromine bond, using the alkene as a nucleophile, and we form our bromonium cationic intermediate, and then attack of the second bromine coming in from, in this case, from the top side, we would get the anti-addition of bromine. So there's our first bromine that added, and there's the second bromine plus the enantiomer again. So again, anti-addition through a three-membered cyclical intermediate. Another example of this type of addition is the halohydrin reaction, where if we take bromine or chlorine, and in the presence of water, we do the reaction. Again, remember we get nucleophilic addition or nucleophilic attack on bromine to form our ammonium cationic intermediate. So in this case, we'll do bromine going away again. And in this case, our nucleophile would be water coming in to attack from the top side. We then need to do a deprotonation, but again, we would see the addition, the anti-addition of water or bromine and a hydroxide plus the enantiomer to form our halo alcohol. So again, three reactions all in the first step, adding something that has lone pairs on it to give me a three-membered cyclic intermediate. So the last reaction I want to talk about is one that is a little bit different because it involves a peroxy acid, but again, we see this three-membered cyclic intermediate. So if we were to take this, and I'm going to kind of draw a weird arrow, and we were to add some kind of peroxy acid, so let me fix that. So RCO3H, so we hit that with peroxy acid, we follow it up with an acidic workup. So remember, the first step in this reaction is the formation of what we call an epoxide. So we'd see our 5-membered cyclic epoxide. So in this case, we'll make that epoxide going away or coming out towards us. Then that epoxide is protonated in this, and we form our oxonium intermediate. So oxonium intermediate. So there's the bond. We'd form our oxonium intermediate. Then we'd go through and add water to the second side as our nucleophile. And here we get the anti-addition of 2 hydroxides. So we would have our cyclopentyl group with 2 hydroxides resulting from anti-addition. So one coming out towards me from the first step, one going away from me from the second step, plus again the enantiomer. So what we have here is an example of what may seem like 4 very different reactions, but remember, in every step we've added a molecule that has lone pairs on it. Big erase. So in every case we form these 3-membered cyclic intermediates. And because of the formation of these intermediates, we see that one side of this newly formed compound is completely blocked. The only clear path for this second nucleophilic attack is from the back side. So all of these result in SN2 type reactions in the second step to give us anti-addition products.